Hello, I'm Hako Kim, working as a postdoc at EPFL. Today I'm going to present our research on towards a better understanding of VR sickness, physical symptom prediction for VR contents. VR sickness is one of motion sickness in virtual environments. According to the studies, approximately 80% to 95% of viewers exposed to VR experience reported some level of VR sickness. And the VR sickness could lead to various types of physical symptoms, including discomfort, fatigue, dizziness, vertigo, and even burping. So the cognitive reaction of a person in watching VR is much more complex than the perception in 2D or 3D image. To measure the level of VR sickness, there are several studies based on the subjective assessment and objective assessment. At first, when you watch VR content, we could feel some level of VR sickness as you have experienced already, and then we could score the perceived sickness level like that. That's a subjective assessment. On the other hand, the objective assessment is like that. The motion perception model analyzes the content properties related to the human perception and then predict the comfort score as close as possible to actual human subject score. If this is possible, the motion perception model can replace the human perception model in various fields. For example, we can provide the level of VR sickness for all contents in VR market automatically. However, there are not much research on content analysis-based objective VR sickness assessments. The first reason why is the lack of large number of VR sickness assessment databases. In most of objective assessment research for human perception prediction, the relation between the contents and the corresponding human response is trained with enough training datasets. But it is very time-consuming and labor-intensive to collect subjects and conduct the extensive subjective experiments. In addition, we have to consider the viewing safety of the subjects participated in our subjective experiments. The second reason is the complexity of VR sickness. According to the existing works, there are at least 16 physical symptoms highly related to VR sickness causes. They can be divided into three major symptoms, which are disorientation, nausea, and oculomotor symptoms. One important problem is that VR contents inducing similar level of VR sickness may have different physical symptom causes of VR sickness. Most recently, there are a few approaches for VR sickness assessment by analyzing the spatial temporal characteristics of contents. However, most of them just predict the level of total VR sickness score or simple mean opinion score instead of physical symptom prediction. So recently, several studies were proposed to evaluate the overall VR sickness level for 360-degree videos. For example, VRSANet, VR sickness predictor, and Deep Cyber sickness predictor. They showed good prediction performance of overall VR sickness score and built a large-scale VR sickness assessment databases. However, they could not provide any idea as to which symptoms are dominant for each 360-degree video. Most recently, symptom-aware cyber sickness assessment network was proposed to investigate the relation between the symptoms of VR sickness. This is the first attempt to analyze the relations between the various physical symptoms of sickness. But this is not practical because it requires physiological measurement in coding. To deal with that, we focused on human perception in VR viewing. This figure represents the mechanism of neural mismatch for VR sickness caused by visual stimulus, which is the most widely accepted theory for VR sickness. So at first, the visual sensory input is sensed by our eyes. Then, neural store in our brain expect the visual sensor information from the past experience that we learned on daily life. In the comparator, these two signals are compared and then mismatched signals are produced. If this mismatch signals level is larger than our tolerance level, we can perceive some level of physical symptoms of VR sickness. That is very reasonable theory. The reason we feel motion sickness when we're riding on a roller coaster or watching roller coaster video with a head-mounted display is because the roller coaster experience is far from what we experienced in our daily life. So the farther we are content from the viewing experience that we normally feel, the more it may cause excessive VR sickness. Based on this mechanism, neural mismatches, we built a novel motion perception model for predicting physical symptom level of VR sickness. It consists of a neural store network, comparison network, and physical symptom score prediction network, which are correspond to each component of neural mismatch mechanism respectively. The neural store network is to predict the next frame with the trained parameters in training. For this purpose, the network is trained with a normal video that can be easily accessed in our daily lives. The comparison network is to compare the input video frames with the expected video frames predicted by the trained neural store network. By encoding the differences between them, the neural mismatch feature is encoded in the comparison network. Finally, the prediction network is to estimate the three major symptom scores by mapping the encoded neural mismatch feature into the subjective score. Okay, at first, the proposed neural store network consists of the previous visual signal encoder, future visual signal predictor for expectation of the next frame, and the discriminator via adversarial learning. Since people generally cannot experience the situation causing severe VR sickness, such as exceptional motion, shaking, and low frame rate, the neural store network is also trained with the normal video sequences. In this work, the normal video sequences mean that the contents do not cause severe VR sickness, and their total sickness scores are under about 30. To teach the neural store network the general experience of people, we use the normal videos without acceleration, rapid rotation change, and shaking, etc. And as the input frames of a neural store network, we use the pleasantly looking normal field of view segments. The proposed previous visual signal encoder and future visual signal predictor consists of convolutional LSTM and the deconvolutional LSTM. By minimizing the difference between the original frame and the expected frame in our prediction loss, the prediction quality can be enhanced. And the second term in the prediction loss helps the predicted frame to be realistic enough to fool the discriminator. Okay. Second, the discriminator is to determine whether the input is realistic or not. The spatial-temporal discriminator is based on the 3D CNN in this work. The d phi ft in the first term is the probability that the discriminator determines the fake sequence as original. The second term is the probability that the discriminator determines the real sequence as original. So by adversarial learning between the predictor and the discriminator, the prediction performance of the neural store network for normal video sequence can be enhanced. Next, our comparison network is designed to encode the mismatch information. After obtaining the expected videos by the trained neural store network, the difference information between the original frame and the predicted frame is encoded, as well as visual information of the input video sequence. The visual feature and the different features are concatenated and encoded to produce the mismatch feature. Finally, in the proposed physical symptom score prediction network, the degree of three major symptoms of sickness are predicted from the latent neural mismatch feature. The symptom score prediction network plays a role in nonlinear mapping the high-dimensional neural mismatch feature space onto the low-dimensional symptom score space. For this purpose, in the training stage, the sickness score for disorientation, nausea, and oculomotor are predicted from the neural mismatch feature by minimizing the objective function between the predicted symptom scores and the ground truth objective scores. In this work, mean sickness score values for disorientation, nausea, and oculomotor obtained from subjects are used as a ground truth physical symptom scores. In testing stage, the expected video frames are obtained by the trained neural store network. Then, through the comparison network and the physical symptom score prediction network, the physical symptom scores are obtained from the original and the expected video sequences. In particular, we built a large-scale physical symptom prediction databases and conducted the extensive subjective assessment experiments. We collected a total of 20 4K 360-degree videos with high frame rates were collected from the Vimeo websites. They contain various moving scenarios such as drone, bike, motorcycle, paragliding, etc. From the 20 360-degree videos, a total of 80 videos were generated using the optical flow interpolation of Adobe Premiere with the target 4 different frame rates, which are 10, 15, 30, and 60 frames per second. And a total of 20 subjects participated in our subjective experiments. Each video was randomly displayed for 60 seconds. The resting time was 90 seconds. During this resting time, subjects were asked to estimate the level of perceived sickness using 16-item simulator sickness questionnaire score sheets. In addition, we measured two physiological signals, heart rate and galvanic skin response. Please refer to our paper and supplementary files for the details on our subjective experiments. This figure shows the distribution of VL sickness score for our new database. The black dot indicates the mean sickness scores for stimuli at each frame rate. As shown in this figure, the sickness score of the 360-degree videos with high frame rates were very low. On the other hand, the total sickness score of the VR content with low frame rates were higher than those of high frame rate content. For performance comparison, we compared our symptom prediction with existing deep autoencoder-based method, optical flow plus our symptom prediction network, and only neural store network plus symptom prediction network. The optical flow map seemed to be effective for predicting disorientation scores. However, it was not good at predicting nausea or oculomotor symptoms. This is because VR content with complex motion patterns or rapid acceleration can lead to inaccurate motion estimation. Then, the inaccurate optical flow information can interfere with the physical symptom score prediction. Compared to all of them, our model outperformed. This figure shows the predicted physical symptom scores by our methods for various datasets. As shown in these figures, videos 7, 11, and 18 include acceleration and rapid rotation in various directions and low frame rates. In case of that, the subjects scored high on disorientation symptoms. On the other hand, video 12, 17, and 20 do not include fast motion, but contains a lot of shaking in the right figure. The predicted physical symptom score indicated that the subject felt severe nausea symptom. when they watch the contents with extreme shaking. This slide also shows additional examples. In case of the left figure, the level of major physical symptoms caused by different VR contents were very similar. It means that 3 different physical symptoms were perceived to a similar level to subjects when they watch these contents. On the other hand, the right figure shows the example of the different major symptoms caused by each content, while these stimuli had a similar level of total sickness scores. Video 9 and 13 with 10 frames per second caused excessive disorientation symptom. Video 14 with 10 frames per second caused excessive nausea symptom, and other symptoms level were similarly higher. Video 19 with 15 frames per second was highly likely to induce excessive disorientation and nausea symptom, both of them. It shows that despite the VR contents causing similar level of total VR sickness, the physical symptoms that they dominantly caused can be different. The results demonstrate that it is essential to predict the physical symptom level of given VR contents in order to better understand VR sickness in watching VR and provide the explainable viewing safety guideline or content creation guideline for VR contents. Finally, Table 2 and 3 shows the prediction performance for overall VR sickness on 2 different VR sickness benchmark databases. Even one of the recent work, VRSANet, could not work when on our new databases because the characteristic of our databases is different from the publicly available databases. However, our model achieved the highest correlation with the human ratings on both benchmark datasets with different characteristics. As a summary, we present a novel physical symptom prediction model based on neural mismatch mechanism for 360-degree videos to make better understanding of VR sickness. We also introduce a new large-scale data set for these fields, including 360-degree videos with various frame rates, physiological signals, and subjective score. Finally, our approach shows a potential to not only achieve good prediction performance, but also to better understand which symptoms are the main causes of VR sickness. Thank you for your attention. Our database will be available on our webpage for database. Thank you.